Hello friends, welcome back to my YouTube channel. Welcome to my discussion on distillation. This is part 19 of that distillation, and from this point of time I am going to start my discussion on McCabe Thiele method. Again, the discussion on McCabe Thiele method is divided into various parts, and this will be the first part of that discussion. Here I'll be talking about what are the assumptions that are used in the McCabe Thiele method. So at the end of this discussion, you'll know what assumptions are used while using McCabe Thiele method. Okay, so let us start the discussion. A brief introduction to McCabe Thiele method. The McCabe Thiele method, it uses only VLE data. For using McCabe Thiele method, there is no need of the enthalpy data. What is required is just the VLE data. It uses only VLE data. What is VLE data? I have already discussed it in my previous videos. Those of you who have not yet seen those videos, please visit my channel. But over here, I will briefly tell you what is VLE data. VLE, it stands for vapor liquid equilibrium. So in order to understand that, if you consider a simple example, what is the example? We are going to consider a liquid solution that is containing two components in it, component A and B, and this liquid solution is in equilibrium with a vapor mixture of the same two components A and B. So you have liquid solution of A and B in equilibrium with vapor mixture of A and B. So we are considering a system in which liquid solution is in equilibrium with vapor mixture. Again, the same two components are involved in the system. So that means you have components A and B in the liquid solution and components A and B in the vapor mixture. Okay, so we are considering a liquid solution of A and B that is in equilibrium with a vapor mixture of A and B. Out of A and B, A is the more volatile component. That means boiling point of A is less than that of B. Since A is considered to be the more volatile component, similarly vapor pressure of A is greater than vapor pressure of B. Okay, so when we say that A is the more volatile component, then A has a lower boiling point than B and it has a higher vapor pressure than B. Okay, so a liquid solution of A and B in equilibrium with vapor mixture of A and B. A is the more volatile component. Then small x and small y, these are mole fractions of A in the liquid and vapor phases respectively. So that is x is mole fraction of A in the liquid solution and y is mole fraction of A in the vapor mixture. And we are saying that liquid and vapor phases, they are in equilibrium with each other. So in this case, x and y, these are equilibrium mole fractions of A. Mole fractions of A in liquid and vapor phases that are in equilibrium with each other. Okay. So each XY pair. What is the meaning of this? That means whenever vapor and liquid phases are in equilibrium, there will be some concentration of A in the liquid phase. The most convenient way of expressing concentration is mole fraction. So X is mole fraction of A in a liquid solution that is in equilibrium with a vapor mixture of A and B, in which Y is mole fraction of E. Okay, so here X is in equilibrium with Y. That means you have one pair of X and Y. So one pair of X and Y defines one equilibrium state. So that's why I'm saying each XY pair defines one equilibrium state. And VLE data then is the collection of many such pairs. The VLE data is collection of many such pairs. So there will be number of X values, there will be number of Y values, and each pair will be defining one equilibrium state for the system. Okay, so this is VLE data, vapor liquid equilibrium data, a collection, a data which has equilibrium concentrations for the more volatile component. And we have understood the concept by taking an example of a binary system, binary liquid. So what is the meaning of binary system? The system that is containing only two components in it, A and B. Okay, so I hope this is clear to you. If you have any doubts, you please let me know in the comment section. Okay, now let us understand what are the assumptions. So we have understood, we had a brief introduction to McCabe Thiele method. It is a kind of simple introduction to McCabe Thiele method, where we have understood that McCabe Thiele method is going to use, or McCabe Thiele method uses only the VLE data, and then we have understood what is VLE data. Okay, now let us start with knowing what are the assumptions. So for that, let us consider a typical tray column. So I have shown a tray column. These dashed lines represent various trays in the tray column. Feed, which is identified by this and parameters. It is entering on a tray, and that tray is the feed plate. Then the feed, after entering on the feed plate, it flows down. It is removed from the bottom, and then it goes at the bottom. It is taken to the reboiler, where it is heated at a rate of QR to create the vapor phase. The resulting vapor phase is admitted at the bottom. The vapor phase then rises through the column. Then it is taken out at the top. It is sent to a condenser, where heat is removed from the vapor at a rate of QC to get a condensate, and that condensate is then divided into two parts. One is taken out as the top product, we call that as distillate, or the top product, and it will be identified by these parameters. And then one fraction of the condensate is sent back to the column as a reflux. Reflux will be identified by these parameters. Then the reflux, after entering on the top tray, will flow down, and on the feed plate it will be joining with the feed solution, and the operation will continue. From the reboiler, we are taking out the bottom product, which is called residue, and it will be identified by this parameter, WXW and HW. Okay, so all H that you are seeing in this schematic diagram, these are enthalpies per unit mole. So for example, if it is HF, this is enthalpy of feed per unit mole. Enthalpy per unit mole of the feed, Then HW is enthalpy per unit mole of the bottom product. So basically H represents enthalpy per unit mole. Okay, so I have discussed this in my previous videos. You please watch those videos, you will understand the concept. Okay, then we also know the section above the feed plate, section of the tray column above the feed plate, it is called rectifying section. So I have discussed in my earlier videos why it is called as rectifying section, and section below the feed plate, it is called as stripping section. Why these sections have these names, I have discussed in my earlier videos. Okay, so let us continue the discussion. Now the first assumption that is used in McCabe Thiele method, the assumption is heat losses from the column are negligible. Heat losses from the column are negligible. That means heat losses to the surroundings, they are negligible. They are very small. They are considered to be very small, so that you can neglect them. Okay. In reality, how can this be done? How can you reduce the heat losses? By providing appropriate insulation. Okay, so in actual operations, the heat losses can be reduced by properly insulating the column. You cannot make them zero, but you can reduce it to a minimum value. Okay, so now what we will do, we will try to understand what is the effect of this assumption, or how this assumption helps us in simplifying the discussion. First assumption, heat losses from the column are negligible. And now we are going to understand what is the effect of this assumption. In order to understand the effect, we will consider the energy balance for the rectifying section. And over here, I'm going to take the equation that I had derived in my previous video while discussing energy balance for a typical tray column. I have discussed the energy balance. So I will take the equation that was derived in that equation. What is that equation? The equation is like this: ln upon gn plus 1, that is equal to yn plus 1 minus xd divided by xn minus xd, that is equal to hgn plus 1 minus q1 divided by hln minus q1. So this equation was derived in the discussion on energy balance for the tray column. You please just watch the discussion. Here Ln stands for the liquid molar flow rate that is leaving nth tray. Gn plus 1 stands for the vapor molar flow rate that leaves n plus 1 tray. Yn plus 1 is mole fraction of A in the vapor flow, in the vapor that has flow rate Gn plus 1. Accordingly, xd is mole fraction of the more volatile component. In this case, it is A in the distillate. Xn is mole fraction of A in the liquid that is leaving nth tray. Hgn plus 1 is molar enthalpy, or mole enthalpy per unit mole of vapors that are leaving n plus 1 tray. Q1, it is the net heat removed at the top of the column per unit mole of distillate. So I have discussed all this. So you please just go and watch that video lecture. So I can simply write this as Ln upon Gn plus 1 is equal to Q1 minus Hgn plus 1 upon Q1 minus HLN. I'm going to give link to the video lecture in which I have discussed this in the description section. Okay, so we had this equation Ln upon Gn plus 1 is equal to Q1 minus Hgn plus 1 upon Q1 minus HLN. So if I rearrange this, how I'm doing that? So I'm adding HLN, and at the same time I'm subtracting it from the in the numerator. So Q1 minus HLN minus HGN plus 1 minus HLN divided by Q1 minus HLN. So that gives us Ln upon Gn plus 1 is equal to Q1 minus HLN divided by Q1 minus HLN minus HGN plus 1 minus HLN divided by Q1 minus HLN. So in this step I have simply separated the denominator. So this denominator I have separated, and now I have two terms. Okay, so in the next term what is going to happen? This is going to get cancelled out. So Q1 minus HL1 will cancel with Q1 minus HL1 in the denominator. So you have this equation, Ln upon Gn plus 1 is equal to Q1 minus HLN divided by Q1 minus HLN minus Hgn plus 1 minus HLN divided by Q1 minus HLN. That gives us Ln upon Gn plus 1 is equal to 1 minus, this is 1, this comes out to be 1. Okay, so 1 minus Hgn plus 1 minus HLN divided by Q1 minus HLN. Now the fact is Q1, which is the net heat removed at the top, it is given as, so if you look at the top, the total heat removed will be the heat removed along with the distillate, it will be D into HD, and the heat removed in the condenser. So Q1 is DHD plus QC into D. So this is net heat removed at the top per mole of the top product, that is per mole of the distillate. Okay. So as compared to the enthalpy of the liquid on nth tray, the heat removed at the top is very large. So that's why I'm saying Q1 is very much larger than HLN. And along with this, if this difference in the enthalpy of vapor and liquid phases, if this difference is substantially constant, then you can say that, or you can conclude that Ln upon Gn plus 1 is also constant. Q1 is very much greater than HLN. The numerator is constant, 1 is constant, so that means the ratio itself is approximately constant if you are assuming negligible heat losses. Okay, so here in our discussion we have not considered any heat loss from the column. We are considering heat associated with various streams and the heat that is removed in the condensed. Okay, so the first assumption that is used in McCabe Thiele method, heat losses from the column are negligible, leads us to this conclusion. The ratio of liquid molar flow rate to vapor molar flow rate, it is constant. Okay, so that is the conclusion, or that is the result of this assumption. Heat losses from the column are negligible. Okay, so we just had got this conclusion. Ln upon Gn plus 1 is constant. You can do a similar analysis and you'll come to the same conclusion for stripping section. Same is true for stripping section of the column. That means for the stripping section, this ratio L bar m divided by G bar m plus 1 is constant. Okay, so here in order to convey the fact that liquid flow, so when you have the column and you have the rectifying section and then the stripping section. Okay, so liquid flow in rectifying section, it is different from that in the stripping section. So if it is L, if L is say molar liquid flow rate, in this rectifying section, it will be different from the liquid flow rate in the stripping section. And in order to show that, we are using this notation L bar yum. L bar indicates that it is different from L. Okay. And same is the understanding with the vapor flow rate. Vapor flow rate, they are different in the two sections. Okay. So at the end of this particular discussion, we have now understood that if you assume heat losses from the column to be negligible, we conclude that the ratio of liquid flow to vapor flow, ratio of molar flow rate of liquid to molar flow rate of vapor in each section, it is constant. Okay, so that was the implication of the first assumption. Then second assumption that is used in McCabe Thiele method is heats of solutions are very small and hence negligible. Okay, so heat, what is the meaning of heat of solution? Let us first understand. So heat of solution is the enthalpy change when a solute dissolves in a solvent. Are you understanding? That means over here, A in the vapor phase, it will be dissolving in the liquid phase, and the enthalpy change associated with this dissolution, it is very small and that can be neglected. So that is the second assumption for second assumption used in McCabe Thiele method. What is that? Heat of solutions are very small and hence they are negligible. And what is the implication or what is the effect of this assumption? If heats of solution are neglected, it again contributes to this result. That means L by G is constant. L by G in each section of the column is constant. This assumption is further strengthened, or this fact is further strengthened with assumption number 2. Assumption number 2 is heats of solution are very small and hence they are negligible. Okay. Then the third assumption that is used in McCabe Thiele method is equimolar overflow and vaporization. So over here, first we'll understand what is the principle of equimolar overflow and vaporization, and then how it is useful, or what is the effect of this assumption, we will understand. So for that, what we will do, we will consider two adjacent plates in the rectifying section, or two adjacent trays in the rectifying section. Okay, so I'm showing that over here. So this is the column, then these are two adjacent trays. This is, let us say, pth tray, tray number P, and this is qth tray. Okay. Now vapor will be coming from the bottom or from the tray below qth tray. So it will be denoted by this notations. It will be GQ plus 1, the molar flow rate, and YQ plus 1 will be mole fraction of A in it. That is mole fraction of more volatile component in it. Okay. Then vapor phase will be rising from qth tray, and now it will be identified. The molar flow rate will be GQ and mole fraction will be YQ. Then after going to peak tray, it will be rising from peak tray, and then it will be having molar flow rate of GP and mole fraction of YP. Now let us talk about the liquid stream. Liquid stream to peak tray comes from the tray above peak tray. So it will be denoted as LP minus 1. So tray before peak tray is P minus 1. So liquid coming from that tray will have a molar flow rate of LP minus 1, and mole fraction of A in it will be XP minus 1. Okay, then from P tray, the liquid stream that will be leaving, it will have a molar flow rate of VLP and mole fraction of A in it will be XP. Similarly, the liquid flow, the liquid that is leaving Q tray will have molar flow rate of VLQ and mole fraction of A, that is more volatile component in it, will be XQ. Okay, so this is our uh, schematic representation of the two adjacent trays that we are going to consider. I am showing it once again. Now I will draw this envelope. If you look at the envelope, if I try to represent it by a rectangular block, let us say that this block is representing the envelope that I have drawn over here, then you can identify four streams associated with it. One is the liquid stream that is coming into it, this stream. Then we have the vapor stream that is coming into it, this stream. Then the vapor stream that is leaving this envelope, that is this stream. And there is another liquid stream that is leaving this envelope, and I'm talking about this stream. Okay, so now you can easily tell that there are two streams that enters the envelope and there are two more streams that leaves the envelope, two liquid streams and two vapor streams. Okay, and if you consider steady state total material balance for this envelope, it will be simply written as input is equal to output. Input is this plus this, so that's why you have LP minus 1, the liquid stream that is entering, plus GQ minus 1, the vapor stream that is entering. Input is equal to output. Output is the vapor stream with flow rate GP that is going out, and the liquid stream with flow rate LQ that is coming out. So that's why the total material balance written for steady state for this particular system is given by this equation: LP minus 1 plus GQ plus 1, that is equal to GP plus LQ. Okay, now let us start with this. So what I'm doing in the next step, I'm dividing by this particular group. What is that group? Throughout the equation, I have divided by this product, GP into GQ plus 1. Okay, so you can just see each term is divided with this group, GP into GQ plus 1. So if that happens, or if you simplify it further, what could be the next step? You can just think about it. Look, if you look at this particular first term, nothing is happening with it, but with the second term, GQ plus 1 gets cancelled out. With this term, GP gets cancelled out, and nothing is going to happen with this term. Okay, so that in the next step you get a simplified equation, that is LP minus 1 divided by GP into GQ plus 1, no change in it, plus 1 upon GP. GQ plus 1 is getting cancelled, that is equal to 1 upon GQ plus 1, GP is getting cancelled, plus LQ upon GP into GQ plus 1. There will be no change in that term. Okay. Now since L by G is constant, which is the case due to the assumption that we had made, the previous two assumptions, heat loss is negligible and heats of solution negligible. So if L by G is constant, that means LP minus 1 upon GP, actually the we had got this thing in our discussion. We had understood Ln upon Gn plus 1 is constant, so that was our conclusion. So if you look at this ratio, you in the numerator you have liquid flow, that is liquid flow rate of the liquid that is leaving nth tray, and this is vapor flow rate that is leaving nth n plus 1 tray. So we want liquid flow of a previous tray. So here LP minus 1 is a previous tray and P is the next tray. So we have liquid flow for P minus 1 tray and vapor flow for P tray, which is equivalent to this. Since this is constant, or this is constant, similarly over here you have LQ, that is liquid flow from Q tray, and vapor flow from Q plus 1 tray. So that is also going to remain constant. Okay, so the point is LP minus 1 divided by GP is equal to LQ divided by GQ plus 1 in the rectifying section. That means in the rectifying section, this ratio of liquid flow coming from a tray to the vapor flow coming from the next tray, that ratio is constant. It is constant throughout the section, throughout the rectifying section. So due to this, what happens? These two terms, they are going to get cancelled out. I hope this is clear to you. Now let me rub this thing. So I have already shown over here. So that means LP minus 1 upon GP is equal to LQ upon GQ plus 1, and that's why these two terms get cancelled. And let us see what happens next. So you have this equation. This is I have already talked about it. So this leads to this equation: 1 upon GP is equal to 1 upon GQ plus 1. Okay. So this was the equation, previously written equation, and then due to the assumption, which assumption? Ln upon Gn plus 1 is constant, we have this equality, and due to this equality, these two terms are getting cancelled and you are left with this equation. So this suggests that Gp is equal to Gq plus 1. Gp is equal to Gq plus 1. Okay, so next, in order in continuing the same discussion, again I am starting with the total material balance for a section which has two adjacent trays in it, and this time I'm dividing each term with this product LP minus 1 into LQ. Okay, so I have done that over here. So you have LP minus 1 upon LP minus 1 into LQ plus GQ plus 1 divided by LP minus 1 into LQ, that is equal to GP upon LP minus 1 into LQ plus LQ upon LP minus 1 into LQ. So in the first term, LP minus 1 is going to get cancelled out and we will be left with 1 upon LQ. Nothing is going to happen with this term. Same thing, nothing is going to happen with this term. It will remain as it is. Whereas in the last term, LQ is going to get cancelled out and we are left with this term 1 upon LP minus 1. Okay, so again, since L by G is constant in the rectifying section, that means Ln upon Gn plus 1 is constant throughout the rectifying section. Okay, the liquid, I have already explained this just now. So due to this, LP minus 1 divided by GP, liquid flow from a tray divided by vapor flow coming from the next tray is constant. So P minus 1 by P and Q upon Q minus 1. So this ratio is going to remain constant. That means each such ratio in rectifying section will have the same value. That is, such ratios will be equal for the rectifying section. Okay. So due to this, what happens? Let us understand. So you have this, and now as per our assumption, previous two assumptions, we have got this. So that means LP minus 1 upon GQ plus 1, or rather LQ upon GQ plus 1. This is 1 upon, in the equation you have this term. The term actually present in the equation is LQ upon G. Just 1 minute, let me just, the equation, the term that is present in the equation is GQ plus 1 divided by LQ, which is a reciprocal of this. Okay. Similarly, on the other side, the term that is present is GP upon LP minus 1, this term. So you just, if you look at this, you have this term, and then you have this term. Okay, so these are reciprocals of this two. Okay, so if the two terms are equal, if the ratio is equal, their reciprocals will also be equal. So with this understanding, what is going to happen? This is going to get cancelled out. On the ratio is going to get cancelled out. So that means you are left with 1 upon LQ, that is equal to 1 upon LP minus 1. Okay, so you have the ratio is constant, and that's why we are left with this. So that gives us LP minus 1 is equal to LQ, which suggests that the liquid flow is also constant. Okay. So in the rectifying section, due to this, we are getting GP is equal to GQ plus 1, and LP minus 1 is equal to LQ. That is, vapor flow entering the section is equal to vapor flow leaving the section. If you remember the section that we had considered, the entering vapor flow is GQ plus 1, and leaving vapor flow is GP, whereas the entering liquid flow is LP minus 1, and the liquid leaving liquid flow is LQ. Okay. So the conclusion is entering vapor flow is equal to leaving vapor flow, and entering liquid flow is equal to leaving liquid flow. Okay. So from this you can conclude that the molar flow rate of vapor phase is same throughout the rectifying section. Similarly, the molar flow rate of the liquid phase, it is same throughout the rectifying section. Okay. So for rectifying section, you can write flow, liquid flow on tray 1 to liquid is equal to liquid flow from tray 2, so on and so forth. Similarly, vapor flow from each tray, they are same, and this is nothing but the principle of equimolar overflow, and vaporization. Okay, so the molar flow rate of vapor phase is same throughout the rectifying section. That is our conclusion. Then molar flow rate of the liquid phase is same throughout the rectifying section, and similar analysis can be done for the stripping section, and you will get the same conclusion. For stripping section also, liquid flow will be same throughout the section, and vapor flow will also be same throughout the section. And this is nothing but what is called the principle of equimolar overflow and vaporization. Okay, so the third assumption that we are talking about is we are now saying, or we are assuming, that principle of equimolar overflow and vaporization is applicable. That is the third assumption used in McCabe Thiele method. Okay, so nobody will ask you to prove why, what are the effects of the assumptions. The way I have shown what is the effect of each of the assumption, you may not, there is no need of uh, telling what is the effect. For you, what is important, you need to remember the assumptions that are made while using McCabe Thiele method. What are the assumptions? Heat losses from the column are negligible, heats of solutions are negligible, and the principle of equimolar overflow and vaporization is applicable. Okay, so with these three assumptions, McCabe Thiele method is used. Okay, and these assumptions, they are known as simplifying assumptions. These assumptions are made to simplify the analysis, simplify the method. Okay, so what is important for you? Important thing that is, you have to remember these assumptions, and if possible, you should also be able to tell what is the effect of this assumption. Okay, so I have discussed those three assumptions, and then I have also discussed what are the effects of this three assumptions. In my next video lecture, I'll be continuing my discussion on McCabe Thiele method. Please subscribe to my channel, tell your friends to subscribe to it, and if you have any doubts, you please mention those doubts in the comment section. Thanks for watching, and do subscribe to my channel. For now, thank you for being with me. Have a nice day, and see you soon in my next video.